We'll be looking at question 18, June 2024 paper. In this question, it's about two oxides of sulfur, sulfur dioxide and sulfur trioxide. It says sulfur trioxide decomposes to form sulfur dioxide and oxygen. You've got the equation there. It's asking you that you've got the initial amount of sulfur trioxide is heated at 550 degrees Celsius in the presence of a catalyst. So the temperature is to get the reaction going, the decomposition going. And as you can see, it's an endothermic reaction from the delta H value. So you get decomposition happening. The equilibrium mixture contains 0.9 moles of sulfur dioxide, and the total pressure is 2.8 atm. It's asking you to calculate the numerical value of Kp and state the units. You see, what we're going to be doing here is we need to use the ICE table, and we need to calculate the mole fraction and use the total pressure to work out the partial pressures. So let's have a go. You've got the equation here, SO3, which gives you SO2 and half O2. Now remember, the ICE table, you got the initial amount. C is for change, and E is for at equilibrium. Let's work this out. The initial amount is 2.25 moles. We have 0 moles of the products at the beginning. And it tells you that you've got 0.900 moles of sulfur dioxide. Can you see that during this reaction, you're gaining 0.900 moles of SO2 because it forms in a 1-to-1 ratio. That means you're going to be subtracting 0.900 here. This gives us 1.35 moles. And here, because you got half O2, for every 0.900 moles forming, you're going to get 0.450 moles, which is half forming of oxygen. So we now have the equilibrium amounts. Now let's work out the mole fraction. What is the mole fraction? It's the mole of the individual chemical in the equilibrium system divided by the total number of moles. So in this case, we got 1.35. What is the total moles here? That's 2.25, 2.7 moles. .35 divided by 2.70, 0.900 divided by 2.70, 0.45 divided by 2.70. This is the mole fraction. You can work that out. And once you've worked that out, you can then multiply it by 2.80, which is, and I'll highlight it here, is the total pressure. Oops. Total pressure. So let's and this in turn will give you the partial pressures. So working this out. 1.40. And the last one, 0.467. So we've got our partial pressures down. What we then do, let's work out the equilibrium. The Kp expression is going to be products, and we use a small p and curved brackets, times the partial pressure of O2, but this time is to the power of half. Wherever the big numbers are, you raise them to the power, over the partial pressure of SO3. What does that give you? 0.933 times 0.467 to the power of half over 1.400. Give your answer to 3 significant figures. That gives you 0.455. In the mark scheme, it tells you that by getting .455 scores you 4 marks out of 5, and the last one is for the units. With the units at the top, you've got ATM multiplied by ATM to the minus half, not minus, to the half over ATM. You can see that these cancel out and you're left with this, ATM to the half. That is your answer. You get 5 marks for that. Moving on. It's asking, explain why T2 is a higher temperature than T1. You see in this question, you've got SO3 decomposing to SO2 and half O2. I'm going to quickly write down the expression to give you a visual of what is happening. You see that the forward reaction is endothermic. We saw that here. The forward reaction is endothermic, and the reverse must be exo. So you see, why is T2 a higher temperature? First of all, if you raise the temperature, the equilibrium will shift to the right-hand side. Why? Is because it gives you let me say that again. If you raise the temperature, the equilibrium will shift to the right-hand side. So raise the temperature, the equilibrium will shift to the right. Why is that? Because the forward reaction is endothermic. So you get those 2 points for the first mark. The second mark is that this idea that by doing this, the Kp value increases. Why does it increase? Because the equilibrium is shifting to the right-hand side, that means the top part of the expression is getting bigger and the bottom part of the expression is getting smaller. You are dividing a bigger number by a smaller number, which in turn will give you a greater Kp value, thus justifying why T2 is actually a higher temperature, because it gives you a higher Kp value, because you get the equilibrium shifting to the right, you get more products and less reactants in the yield. Moving on. It's asking how is the value of Kp would change if the reaction was repeated with no catalyst added and the pressure of the system increased. There's a rule, ladies and gentlemen, Kp or Kc is only affected by temperature. This may be a trick question. There is no change in either case for the value of Kp. Next question is asking, explain why the bond angle in SO3 is 120 degrees. You see, with sulfur trioxide, sulfur is in group 6. You get an expansion of the octet, and you end up getting 3 double bonds, which are the 3 double bonds spread as far apart as possible using the electron pair repulsion theory, which gives rise to a flat molecule with a bond angle of 360 divided by 3, which is 120 degree bond angle. So how would you put that into words? You just say, because there are 3 double bonds. 3 double bonds, which repel each other as far apart as possible. Explain why both SO2 and SO3 have polar bonds, but only SO2 has polar molecules. To get a visual, let's draw these out. You see, SO2 looks like this. Got a lone pair on the top. You see, if you look at the periodic table, oxygen is closer to fluorine, and oxygen is more electronegative. Oxygen is more electronegative than sulfur. 1 mark. That's the explanation of why they have polar bonds. So this is delta positive because these are delta negative. Now the thing is, you see, sulfur dioxide is not symmetrical. So one side of the molecule is going to be delta negative, and the other side of the molecule is going to be delta positive. Why? Because it is asymmetrical or non-symmetrical. Well, asymmetrical. Whereas it should be a double M. Whereas sulfur trioxide is symmetrical. And in this case, the dipoles cancel out. Imagine all the oxygens are pulling on the sulfur equally. The sulfur is not going to move because all the forces cancel each other out. So in reality, this is a non-polar molecule because the dipoles cancel out. So the first one, sulfur dioxide, is asymmetrical. Dipoles don't cancel out. You could either say that statement or that sulfur trioxide is symmetrical and dipoles do cancel out. With that, ladies and gentlemen, I'll see you next time.